Good afternoon, everyone. Welcome to the presentation. I'm very happy to have so many people here. Perhaps this is an unusual presentation for the McGill AMR Center, but I hope we have a chance to show you a tool, I think, that could be part of the overall tool set of the AMR community to deal with this very pressing problem. So again, there are three of us who will make a presentation. We'll do it very quickly in series. First, I'll cover a few details, primarily focusing on the background that ultimately led to where we are now in our research. Heloisa, this will be followed up by Bernhard, who will cover some of the material that sets the groundwork for a lot of the components that had to come together to develop the model that we call HydroFATE. And then we're going to step in the background because Heloisa deserves the credit for putting all of this together. Heloisa, being both an engineer and now an expert in geography, brings together all that expertise to really produce something that I think is going to be quite powerful over the long term. So I'm going to focus really at the start, just saying there's a natural connection, of course, between human consumption patterns, human activities, and of course everything else that's in the world around us. Importantly, you can see here we have the river surface waters, lakes, etc., groundwaters, and they're all impacted by human activities ranging from agricultural sources to urban sources, and as part of urban sources, all the household sources. So when we consume all this water, but also not just consume water, consume and use many other products, including things like pharmaceuticals, antibiotics, etc., they're residues ultimately that can make their way into the water courses. A large fraction of those, we hope, and particularly in urban communities, goes through wastewater treatment facilities. But a lot of the wastewater treatment facilities, pretty well all wastewater treatment facilities that are around the world, they're really designed effectively to take out the big stuff, not the small stuff. It's not the emerging contaminants of great and growing concern around the world, including pharmaceuticals and antibiotics. And so when all these materials treated wastewaters, they're as an effluent that ends up often in the surface waters here, they gravitate to other locations, and of course they represent a source of potable water for our day-to-day water consumption, our industrial process, etc. And of course they're also a source of water for agricultural use, etc. So the whole thing is all linked directly together. So where we came from, and this is my last slide, is really just to show you an evolution of a program, and I was just reviewing this today, that really started with an idea that's happened back in around 2005, so a little over 20 years ago. I come from a wastewater treatment background, so I'm a chemical engineer by training, an environmental engineer by master's and PhD, and I work in civil engineering, so I'm really not an expert at anything, as I think will become evident over the course of this presentation. But the one thing that I did starting out in my career is I was building on my chemical engineering background by using enzymes that have been separated from microbial and fungal sources as well as plant sources, and using them to catalyze reactions that otherwise were very slow or really just would not occur without their presence. And so I was taking these enzymes, and I recognized the value of enzymes was to actually catalyze reactions at extremely low concentrations. And so early on, this is going back around 2005, is could these start to deal with some of the contaminants of emerging concern, which only at that time were starting to be detected. And so one of the very first things that I started with was estrogens. And so working initially with phenols in industrial waste, I transferred over to now exploring the use of these oxidative enzymes to treat contaminants of emerging concern, again focusing on estrogens. Then one of those, I don't know, fortunate things that happened in research, my graduate student, my PhD student, Usman, broke his hand playing rugby. Fortunate, right? Well, what it meant was somebody who was spending a lot of his day in a laboratory pipetting could no longer pipette. And so we were sitting in my office one day and saying, well, you're kind of out of the lab for at least 6 months. What can we start working on that maybe would complement the other work that you're doing? And the thing we realized is back at that time, because of the lack of detection techniques and really field studies, we started to wonder exactly how much estrogens would be arriving at some of our wastewater treatment plants, and were we then testing our enzyme at realistic concentrations that could be used? So this started a whole process. We started to realize, what are all the various sources of estrogens? The natural estrogens that we excrete from our bodies on a day-to-day basis, which of course differs depending on your gender, etc. But also there are other sources of these estrogens, such as the consumption of, say, the birth control pill. And there was even starting to be claims in the world out there, particularly in the United States, where people who are against birth control were now using that narrative to say, oh, birth control doesn't just kill people, it kills fish. So they were using the environmental repercussions to look into this. So we decided to to delve into this and see, could we actually predict the amount of estrogens based on demographics of the population, but also their consumption behavior, in this case of birth control. But then birth control pills are just one of a whole series of facets of other forms of birth control. So then we had to explore the literature in terms of birth control methods, and of course all the issues of the biology of a woman and different periods of the season, etc., when there would be different levels of excretion. Got to be a very, very complicated issue. But ultimately we ended up with is a model that we published starting, I guess it was 2006, that we could actually predict relatively accurately the estrogen concentrations that were total estrogen load arriving at wastewater treatment plants. This led to an offshoot where we started to realize that if you can predict what arrives at the wastewater treatment plant, can we not then measure what adds to the wastewater treatment plant to assess upstream what your population is doing? And that led to offshoots here. So one, we were using metabolite measurements then to assess the behavior of the population. So in this case, we realized, oh, illicit drugs. We could measure metabolites of illicit drugs, and rather than relying on seizure records and hospitalizations and things like that to determine the level of use and abuse of illicit drugs, we could actually literally hour by hour, day by day, measure metabolite concentrations, and it could be used as an intervention to actually look at whether your interventions to change the behavior of your community were successful or not, without relying on all these other records that are just kind of spot checks. So there was a valuable source of information, believe it or not, in the wastewater itself. And that led us to this other study to say, but yes, now if we know, for example, in the case of estrogens, what's arriving, let's test the assumption that the birth control pill matters. And we started to test what policy implications would be. And so we modeled 11 million users of the birth control pill in the United States and said, imagine if, for some reason, the right-wing government got in the way, and they decided to ban the pill. What would this be? And so we started modeling how people shift their contraceptive choices based on medical literature, and then modeled out what the total estrogen loads would be in the wastewaters. And we saw that there'd be a 170% increase in estrogens in the wastewater if there was a policy implication of changing or diverting away from the birth control. Now it's still a make-up virtual situation, but it shows by eliminating birth control pill, you don't eliminate the estrogenicity. All this connects to the fact that the environmental waste, the wastewater that's being produced, is a rich source of information, and it can be an information that could help you actually judge the value of your interventions upstream. Nothing to do with antibiotics at this point, but I want you to remember the kind of the connection between all these pieces. So this was an offshoot here, but we went back in and said, okay, if we know how many, not just of estrogens, we started to look at 335 different pharmaceuticals that are out there. We estimated how much of these would be produced in wastewaters, how much would be released, and also how much would end up in sludges that would end up on agricultural land and the potential impact that they could have. And then of that 335, we started looking at them relative to measures of potential impact and narrowed down the choice to say that we think that the majority of these are actually not an issue, but there's 14 in particular that we think are deserving attention. And the thing is, when they were deserving attention, they weren't actually being monitored. So there's something else that happens in our research community is people generally follow the methods. So if you have methods that are developed to detect things, what we are realizing is that everybody is following the direction of what is easily measured rather than looking at the things that needed to be observed. And so I think there's another lesson out of this overall picture. We work with some colleagues in the FDA, though, to say, what happens, should we be worried, for example, if people are flushing their unused pharmaceuticals down the drain? And so we used our modeling techniques to say, oh, we think that what is arriving outside in the surface waters is actually not of a very significant impact. However, there still were a number of pharmaceuticals that we deemed to be important, and there needed to be monitoring programs to actually determine whether that was the case or not. But that was a fake simulation, because we were using typical dilutions that for regulatory purposes, we often assume 10-fold dilution of a wastewater once it's put into a river. And so we're using that as a metric then to determine potential impact. But we know very well that it's a much more complicated system than that. That there's all these flows intersecting with all these different wastewaters at every point upstream, and all of these streams intersect and dilute with each other, and of course there's decay of those contaminants as you go downstream. And so we started to ask the question is, can we develop a contaminant fate model that would actually track the presence of these compounds in a larger body? And then we started to upscale it from the local to regional and national scales. At the regional scale, with the support of Environment Canada and Health Canada, we received a contract to actually help test the viability of the method. And then we scaled it up to the country level. Then we got really ambitious and said, if we can do it at the country level, can we do it at a global level? So can we model the entire Earth's surface waters to actually predict for certain emerging contaminants what the potential impact of those might be? And it was our student, Usman, who broke his hand and launched this whole thing that started to talk to Bernhard and one of his graduate students at the time and brought us together, and we started to realize that we could work together, and there was a complementarity between the type of work that I was pursuing with my graduate students and the immense capability that I developed in his group. And so at this point, I'm just going to hand it off now to Bernhard so that he can cover kind of more of that background from his perspective.
You tell me if there's comments online who can't hear me. Hello. So I'm Bernhard Lehner. You've heard before. Elsewhere echoing. So I'm from geography. Maybe I should start by saying I'm only wearing a jacket to events like this. Either if I get an award, which has never happened, so don't worry, or if I'm a little insecure, because I feel I'm a hydrologist and I don't know much about AMR from education. I worked my way into it a little bit, but my background is purely hydrology, not even engineering version. I'm one environmental hydrologist, so I can translate rainfall into river flow. But turns out I have a role in this team that might be useful. And it's true that you heard the history. I was approached long ago by a student of Jim's, and it was all about this kind of data that we produce. So I did my education as a normal field hydrologist, maybe, and then my PhD as a global, large-scale hydrologist. But normally I would work with models that are used to predict water scarcity in the world, how is water availability changing with climate change. And still for all that we needed input data, and that's my niche research maybe today, that I develop a lot of data sets that are used by the hydrologic community to make water flow across the landscape and test what happens. And the main product, in part I'm also hinting at products that Heloisa will use then, is called HydroFATE. It's a river network at very high spatial resolution. We create it from elevation data that we have from satellite remote imagery. We can today produce at a 30-meter pixel resolution anywhere in the world, and that drives the river networks that we create. As a hydrologist, I was then, over long time scales, you see 2013 to 19, we developed a lot of attribute information that comes in very handy now, including key one, discharge, so how much water is in the river, not only where they are, that was from the elevation data, this is now a hydrologic model behind it, how much river flow do we have, although currently we only have this as a long-term average, static, we cannot model dynamics easily. And then we have other information that also is key for the work, is included lakes, for example, where contaminants change really, they sit there, they have a much longer time to decay. So as far as we know, the only model that has over 1 million lakes explicitly inside the model, and we can simulate processes inside. This, I don't want to bore you with this, just a hint of it also plays a role in this research, is how do we work from a modeling perspective? How do we make water or stuff, pharmaceuticals, chemicals, flow along the river network? So we developed an approach. It's not about the numbers here. We let water flow along river reaches. There's like 10 million of them. But because we compute scenarios, we need to be really fast. So it's a bit about the coding. Our model is a bit unique in the way it runs. It's extremely fast, so we can make a very quick global run and repeat that and test different things by doing so. So with all this, we embarked. You heard a bit of it. We started. It's very opportunistic. We had a contact at one point with Health Canada and Environment Canada. That's over 10 years ago. And so we tried out if a model like that could be developed with now chemicals on it. This is for southern Quebec and parts of Ontario. We took some data that we had, consumption data for some pharmaceuticals, and it turned out to be, I would even argue, better than we thought we can do this. So we expanded. I put another grad student on to try out, also opportunistic because he was from Nepal. He wanted to study that region. We used diclofenac because there was data available just to see if the model works. And we started to implement even more data, like wastewater treatment plants in this case. Again, results were really promising. We could test some. We were not too bad in this modeling exercise, so we went on to China next, had another PhD student from there who helped us find the locations of wastewater treatment plants. And that became a main ingredient for us to work with. And also we noticed, particularly in China, those people who are not hooked up, if you want, to treatment plants, what to do with them. So we built in pre-graduate students, even of Heloisa, mechanistics of how to treat, or how to at least include that. It's very difficult. And the last slides I have is a preemptive, like just to round out the story, but you hear much more about this. We then wanted to go global, and that's where Heloisa came in as a PhD student, now postdoc, to make this model really run fully globally. The first piece we needed, no one has had that before, is a wastewater treatment plant database. Where are they even? So we hear more about that. But this was the key ingredient to make it possible to simulate chemicals now, or pharmaceuticals, and their fate on a global scale. You will hear much more about this, so this is just to end the history here, if you want. And I now hand over to the real expert that is between us.
Thank you for the introduction. I came along to try to get all this contaminant fate modeling global. And right now I'll talk how this model works and what was our study with antibiotics. So first of all, a quick reminder of the problem that made us create HydroFATE is that there are contaminants in the water, and they are residual from human activities, and conventional wastewater treatment they're not designed to remove them. So they end up being continuous release to the environment. And those are relatively new substances, so that's why we call them emergent contaminants. And those include pharmaceuticals, pesticides, household chemicals, personal care products, microplastics, and PFAS. And one thing about these substances is that they can have a potential impact on aquatic ecosystems and also the human health. And even if they have been detected in considerable amounts in the environment, they're still not regularly monitored because there's new ones being created every day and marketed, so we can't keep up. As an alternative to monitoring, since we cannot monitor everywhere in the world, is to use contaminant fate models. And those are used to predict concentrations of these contaminants based on the population distribution and how much they consume and their contaminant pathways to rivers. They can have different scales. They can be local from just one river basin, or they can have regional, country scale, or a full continent. And in our case, we're working with global scales. So one important thing about global contaminant fate models is that they will never be as precise as local models. We use data sets that have to be at least a little bit consistent globally, and we know that there are data biases in countries. But also there's uncertainties in the processes, since we have to simplify a lot of the processes in order to work globally. Still, it is very important to know where water pollution at a global scale, since we can assess the compounding effects with other global issues such as climate change, water scarcity, and in this case, AMR, that we know that antimicrobial resistance is a problem. It's a global problem. And also, we can create information for countries where you don't have enough information to make decisions. So in summary, the goal of these large-scale models is to serve as screening tools to identify substances of greatest risk and areas of the highest risk of contamination. So with that in mind, we developed HydroFATE. So using an example of a pharmaceutical, of an antibiotic, first the model works by estimating the amount that contaminant emission by using the consumption data per capita, which then we apply to the global population, so how it's distributed around the world. And then every step causes the reduction of the contaminant amount. So first you have the metabolism in the body, and then it gets excreted to the wastewater system, and that could be treated or untreated depending on where you are. If it's treated, we apply a removal efficiency. If it's not treated, there's natural attenuation, so there are biological processes in the soil. And then we also, when it then reaches rivers and lakes, we have also decay inside the water in the rivers, and we apply this by accumulating this contaminant downstream until you reach oceans and inland sinks, like lakes that doesn't have an outlet. And in this way, we can calculate the concentration of this contaminant in every river in the world. Some of the characteristics of HydroFATE is some that Bernhard and Jim mentioned, is that it has a high spatial resolution in comparison to similar models. We can specifically see the specific rivers instead of big pixels. It has the drawback is that it has a long-term average, so we cannot use for discrete events, but more of a baseline continuous release. It is based on a global river network, so it has a lot of, it's easily connected with other data sets that already exist. And it is the first model that uses the global database of wastewater treatment plants, which has a specific location of each one of those facilities. But it also includes untreated wastewater, as Bernhard mentioned. So about the HydroWaste database, we started doing that by compiling existing databases that are free online, and those are national, regional, NGOs, open data sets. And we end up with a total of more than 58,000 facilities. So each point in this map is one wastewater treatment plant. The size and the color means almost the size in terms of population that it serves. So each one of them, it will have the location, the population served, and the level of treatment, and that can be used in the model. But also one of the important things is that we estimated not only having the location, but also the location of discharge, so making that connection between the wastewater and the river, so we can create the pathways. And that's how I want to explain a little bit about the pathways, is that now that we have the wastewater treatment plants, we can assign each person, which is the source, to a contaminant pathway. So looking at here is a river reach and a river catchment. And the grid represents population. So each pixel has a number of people inside, and the darker, the gray, more people. So for example, the first pathway is the wastewater treatment plant. There's the dark triangle. We delineated the area, and we assigned the population as a source to the river reach. And then you also have a second pathway, is the people that are not connected to wastewater treatment plants, but they're still treated. It could be septic tanks or any other decentralized treatment. And then we have the untreated populations. We have urban and they can be rural. They have different ways that we apply the associated process of contaminant reduction before it reaches the river. So the selection of how each person was connected to a specific pathway was done. That was the biggest part of the work, and it does by it's all by geospatial methods, also sanitation statistics, to make sure we did the best work possible here. And that was done for more than 8 million individual river catchments. So now that we have the model and all the pathways, we did our first test, and for that we used the antibiotic sulfamethoxazole. We chose it because that's the best data we could find. There's a lot of studies on sulfamethoxazole. We could find measurements to validate the model. We could find consumption per capita based on sales. And that's running the model. That's our first example of how the concentration was distributed. So in this map, you have the color represents the concentration, the darker red, the higher concentration. And in total, of a consumption of 2.6 million kilograms per year, more than 200,000 kilograms per year reaches the rivers. And that one interesting thing is that 71% actually comes from untreated sources. So having these numbers now that we predicted, we were able to do some validation, see how well the model works. And for that, we found more than 200 field measurements. And here we did a simple comparison between measurements in the x-axis and predictions in the y-axis and try to see if they agree with each other. And we got 79% within one order of magnitude. That might seem not good, but think about all the uncertainties that we have in this modeling, and not only in the modeling, but also in the measurements. The measurements, we don't know exactly, we got it from different studies, they have different methods, different times of the year that they got measured, so it's harder to really be a one-to-one comparison between them. So now that we had our first test, we look, how could we do that in more of a larger extent? We want to see what's the total exposure of antibiotics. So first, just a quick why antibiotics are important if they are in rivers, is that same as other pharmaceuticals, they have ecotoxicological effects on the aquatic ecosystem, but they also have that added antimicrobial resistant problem. So they favor an exposure of these organisms to low but persistent levels of antibiotics. And that gives the competitive advantage to bacteria carrying resistant genes. You see that that's not my expertise, knowing the mechanisms exactly how that happens, but we use risk thresholds to try to model the risk of that happening in the river network. And here I just show a little bit more how MR can be a problem that is not only for human health and aquatic ecosystem, but other problems as well for a sustainable future. As sources of antibiotics that come to rivers, we have three main ones. You have the domestic wastewaters that come treated or untreated. We have veterinary runoff that come from livestock activities. And we have industrial discharges that can be from the manufacturing of those compounds or even in other processes that use these compounds in their production. Not that I am dismissing the other one, saying it's not important, but as we mentioned before, HydroFATE only has wastewater as a source for now. I will go back to it in the end of the presentation. But in this study, we only used the wastewaters as a source. So every time I talk about predicted amounts, predicted concentrations, it's only concerning domestic wastewaters. So for that, I'll ask a few questions. Where is the highest exposure to antibiotics in the global river network? And which are the antibiotics that cause the most risk? And for that, what do we need? First, we need the model parameters, same as we did for the sulfamethoxazole. We need consumption, we need the excretion fraction, how much the body metabolizes. We need wastewater removal efficiency, how much the decays in rivers. We also need to validate the model for multiple substances because we only did a test. How does the model behaves using for other compounds? And also we need to know some risk assessment thresholds of AMR and environment. So for the model parameters, it ended up the sulfamethoxazole was a fluke. It was the best one, and the other ones were really hard to find. So we end up, even if there's a lot of antibiotics, we had to focus on 40. But still those 40, they are 90% of the global consumption, so we felt like we did a good representation. And we used the same study that gave us the consumption per capita based on sales as the consumption data. So here's how this consumption is distributed, so we don't have for every country. Some countries have more than others, and the ones that we didn't have any data, we extrapolated based on income classes the best that we could. And so in total, we had 29,000 tons per year of consumption of antibiotics. And all the other parameters were collected from literature as much as we could, and if we couldn't, we used methods to estimate. So for validation, we found measurements for 22 of those 40 antibiotics, and we did a similar comparison like we did for sulfamethoxazole with measurements and predictions, and we see that there's a lot more scatter here than the other one, but remember, added more antibiotics, more data that is uncertain, more uncertainty, harder to predict. So I did end up doing a further analysis on the biggest, the outliers here, and they all were they were all conditions that were not covered by the model. For example, they were measured during high flows. Our model only does average or low. Also, they were measured in locations with heavy veterinary activity or industrial, and that was all based on going back to the measurement study and seeing if they mention anything, and that what makes us see that the model is good if you have average flow conditions average flow conditions and for average situations. And that's due to the way that the model is structured and the data input that we have. So as to start answering our questions, we started mapping the pathways of how the antibiotics are in the rivers. And so here you have from source to sink. So you have in the left you have the wastewaters, and in the right you have the sink, and that could be what is removed and what it gets to the final destination. So that can be very confusing, but that's all how the contaminant moves around within the model. And I'm not going to talk about many of this, but like some of the important numbers here is that we have 43% of the population of this amount is treated, the rest is untreated, and you have and that removes 72% of that wastewater. But also, the untreated wastewater has a lot of removal on land, we call here. And that is very uncertain, also because of the soil processes. But also, doesn't mean that it disappears. It just shifts the problem. But we're looking at rivers here, so still we have 46% of what arrives in the wastewaters ends up in rivers. And that's 9,500 tons per year. So now looking at, instead of looking at total loads, looking at the risk of these substances. For environment, there are two thresholds that we can use. They're both PNACs, predicted no effect concentrations, so they're a protective threshold. One is for ecosystems, so they are derived from toxicity data. They are based on laboratory studies on fish, algae, and invertebrates. And the second one is the MIC, which is minimum inhibitory concentration, and they should be protective of AMR. And they are the maximum concentration that you see no growth of bacteria. And to calculate the risk, I divided the predicted concentration that we got from the model by the lowest PNAC of those two to be protective of both. And we aggregated that risk quotient that was calculated for each substance for all of them. And that's how we get this map, where we show the total risk quotient in every river. So here you see that the darker the red, the higher the risk. And whatever is red or dark red, it is in high risk. So as I mentioned, there was 9,500 tons released to rivers. From that, 3.2 reach oceans and inland sinks. And 6 million kilometers of rivers are at high risk, which is the red and dark red. And some countries, such as India, Nigeria, they have more than 80% of their rivers at risk, and based on this analysis. Now to answer which substance was causing the most risk, in this map, the colors represent the 7 antibiotics that we predicted as the main contributors. The top 3 were amoxicillin, ceftriaxone, and cefixime, which are not usually monitored. So that was one of our big answers here. Now, we also wanted to look at human risk, but beyond AMR, also just the fact that this water contains antibiotics that we're taking. So here we assume that a person consumes water directly from the river without further treatment, no drinking water treatment. And see, like, if we drink the water from the river, how much do we intake of antibiotics? With that, we calculated what we called a dose equivalent. So we divide the predicted concentration by a defined daily dose to see how much are we having of antibiotics. And we aggregated that for all substances similarly. So that's what we got. And so here you see the microdose per liter would be, if you drink 1 liter from one water that is 1 microdose per liter, you're going to have 1 microdose of an antibiotic. Here it's a lot less striking than the other one. And that's also, we're looking at microdoses, and we can say, oh, but a microdose doesn't matter. But the thing is that I forgot what I was going to say, sorry. There's not enough research on the impact of this continuous exposure. So usually when we take an antibiotic, it's to kill an organism, and there's not enough research on the human health when taking this continuously as like a chronic exposure. And one interesting thing is that since we didn't have a threshold, we just calculated what would be the 95th percentile, like the highest concentrations we can find in the world. And actually, 1/3 of the population lives close to areas that have those rivers. What does that mean? We don't know. As I said, there's no threshold, but it's still the pattern is the same. So if the population keeps increasing and the antibiotic consumption keeps increasing as well, that pattern will continue and we will only get stronger. Now, that was the work that we did, but we still have more going on now because we want to go further into especially finding out about the other sources. So HydroFATE was initially only accounting for domestic sources, as I mentioned, but we want to expand it to include agricultural, industrial sources. But there are big challenges, and that's because there's no data. And also, the process is a lot more complex, not only on the transport, but also the decay of these substances before reaching the river. So we are ongoing now with a study, the first test of the veterinary for Canada. We are collaborating with the Public Health Agency to get veterinary antimicrobial sales data. And this figure shows an example of this data highlighting the antibiotic consumption across different livestock categories. So you see the pigs are the highest consumers of antibiotics. And one interesting thing is that when we compare the use of veterinary use with the human use, veterinary is 20 times greater than the human use. And then made me feel, why did I did all that work on the humans if the veterinary is a lot worse? But then there's another question is how much actually reaches the surface waters? Because it is a lot more complex because domestic wastewater, it typically flows directly into the treatment systems and then to the rivers. And livestock operations involve more complex environmental process. There's soil absorption, there's distance to the rivers, there's timing and precipitation. It depends on the timing of the that they are using the antibiotics a lot more than human. And right now, that's what we're trying to integrate to our model, to try to see if that 20 times greater does make that difference. But one thing that we can do even before knowing how much we have is how many kilometers of river are potentially impacted by veterinary antibiotics. So that is just like this figure just shows the distribution of pig farming in Canada. And you notice that there's very small areas in Canada that you do have pigs. For example, you have a little bit in Alberta, you have in Manitoba, Quebec, Ontario. And based on this pattern, our hypothesis is that while there are some rivers that will have very elevated at some points in time, this level of antibiotics, overall, it's going to be very concentrated and in a small percentage of rivers in comparison to the human. This is still valuable. Just knowing where those rivers are, it can already help us point where we should have more targeted strategies and trying to reduce the contamination. But it's a lot easier than the population, human population. Another study that we're going to do is we want to estimate the antibiotic loads entering wastewater treatment plants in Canada and United States. Why only those two countries is because there's updated data on wastewater treatment plants and more granular data, so we're maybe able to get a better picture of those two countries and try to identify hotspots for AMR development in the facilities before reaching rivers. Also, beyond antibiotics, we have other HydroFATE projects. It's not only for pharmaceuticals. We're in the beginning of very early stages of trying to evaluate pesticides at the global scale. We have a partnership with a colleague from Germany that has data, just lacking funding. So yeah, that's where we are. And the second one is ongoing and is going really well. It's let's see if I have a better explanation. Okay. We're modeling a mixture of 80 substances that represent the typical wastewater, European wastewater. So we simulate how substances are transported downstream from wastewater to rivers. And what's interesting about this one is that these 80 substances, they're not only pharmaceuticals, but they include PFAS, food additives, other chemicals, industrial chemicals that we haven't used before. So we're expanding the potential of HydroFATE. And talking about potential, is where do we see all these results being used? And first of all, the easiest one is to guide field measurements and studies. We can see where the data gaps are and how we want to, where we should be focusing our efforts. We can also be used to evaluate legacy substances and prioritize actions to those specific substances. It can be used to support new guidelines, regulations, and policies. It can be used to inform treatment standards and techniques for specific substances that were detected as the highest risk. It can, if we know that the substances that are very persistent and that they are very much spread out in the river network, it can also be used to support the development of less problematic and faster degrading substances, and also identify wastewater treatment plants that should be upgraded based on the location of where they would have the most impact on reducing risk, or even where could we have more wastewater treatment plants. And some of them might seem a little far-fetched, but still we think that the problem of water pollution, AMR, they sometimes seem so huge and complex that I think HydroFATE can help push the needle a little bit more into protecting water and health in the world. So if you have any questions, if you can answer today, you can contact any of us. And also we have a website that has that has all the information about the model and all the publications, and also a web map that has that you can play with different scenarios and different model parameters to see how the model acts with different ones, and also see how the resolution works with the river. So it's very fun to play. Well, thank you.
On stage, first one is Dr. Suzanne Kramer, who's coming from Environment and Climate Change Canada, from the Aquatic Contaminant Research Division. Then we have Sigrun Kulik from the Public Health Agency of Canada. She's part of the AMR task force, and within the AMR task force, one of her claim of fame is she wrote the environmental surveillance and strategy framework.
With a team.
With a team, that she led the effort. And Professor Jennifer Ronholm, she is the CRC chair in agricultural microbiology here at McGill from the Department of Animal Sciences and Food Sciences. Actually, maybe the first two questions I could direct to you three, from what we saw and your expertise, what you're interested in, where data like these or model could take, or what you're interested in, and where's the intersection of what you're doing and
Am I starting? Okay.
environmental data.
Hi. So for me, I do a lot of work on tracking and tracing resistance genes in receiving environments, so rivers and lakes, and kind of trying to understand how they come from source environments, such as wastewater, but also agricultural runoff. We heard a lot about that already. So for me, what would be interesting is, you kind of alluded to it, treating resistance gene like another aquatic contaminant, and kind of seeing, can we actually go from a source such as, human feces, for example, through the wastewater treatment plant into receiving water. So that's one aspect for sure. And another one is definitely looking at relationships between in situ concentration of antibiotics and resistance genes, because we kind of assume by and large that there isn't in situ selection happening. But maybe if you have really high concentration, who knows what's happening? So I guess that's, from my perspective, really interesting.
My interests are similar, but I come from the broader. The Public Health Agency, is the lead for aggregating data on this, and we're going to have to come up with some good data out of the environment. So I'm also particularly interested in the risk aspect, so which ones to be prioritized. There isn't a good international consensus on the targets. Some of this will have to obviously be driven by the situation in Canada. What are we seeing in the clinic? What are we seeing in general? What are we seeing in veterinary? But this is probably going to be quite helpful, because it gives us an idea of what substances we might want to think about a little more in depth. Personally, I was really excited to come here today because so I live in Ottawa. This sounds like I live in the city. No, I live on a dirt road. I stepped out of the door first thing this morning, and the first thing that hits my nose is a strong smell of liquid manure. So, and it was being applied to fields that are still snow covered. A lot of them are no-till fields, which means it doesn't get plowed in. If I'm really lucky, there might be a slit cut in and it goes in there, but I'm thinking not by the way that smelled. We've got precipitation in the forecast in the next couple of days. And this is going on to tiled fields, which means there's huge drainage pipes under these fields. It then goes into our local ditches from where it's pumped into, well, which river? I don't know. But is it going into the Rideau River? Is it going into the South Nation River? Where is this going? And then how important, the big question here is, how important is that? Which which of these risks do I worry about the most? Where, and it's similar to what Suzanne said, where do we focus our efforts, that nexus? And can you identify the spot where that runoff and those pesticides, which might also be co-selectant or cross-resistance promoting, and then the hospital effluent, all of that, where that really comes together, and where's that close to somewhere where you might take your kid to the beach? So if we can do those kind of things, I would love that. So my initial thoughts.
Thank you. My initial thought was, wow, good work. What a cool project, and what, like, tons of data in there. And I'm really happy you started with human medicine, because I feel like once you move to agriculture, there's just so much variables that it's like, learn to live with frustration. But I think where it intersects with my research is I'm really interested in ARG generation on farms and how all the antibiotic resistance genes we generate on farms through the usage make their way into the human population. Like, is it our food? Is it the soil? Is it the water? Is it the farmers? Is it wildlife? And like, where's our best intervention point? But like, we don't have enough data points to figure out how this movement is happening. So like, models like these get us maybe like one or two steps closer to figuring out the intervention points that are going to make a difference in the movement of the ARGs. Cool project.
Good. So we've seen data that could be obtained from private sources or and then modeled geographically and within hydrology. Is there a place for other maybe non-traditional type of data? Public citizens feeding into this effort, or is there a way to integrate, or how do we integrate more data that may not be of natural or typical sources?
We're hearing a lot about sales data, and it's great. I mean, it's not fantastic. It's super expensive, as you pointed out, especially often we have to pay for it. We also pay for it. And we do publish what we can, but it's to go into granularity is really expensive. And we don't have use data, with the exception of maybe for aquaculture. But other than that, we like, if you buy this in Calgary, I don't know if you're using it to the east of Calgary, to the west of Calgary. I don't, in a cattle farm, I don't know that, right? Like, I have no idea. Similar with pesticides, I have those at the national level. I don't know where these azole fungicides are being used and in what quantities. So for that, I think, and it's actually similar with the drugs. Like, we have the sales volume, but they might be stockpiled in a hospital, or they might be being used. I don't know. So maybe on the use side, that would be really, really interesting to get a better understanding of what the actual use is. So from, like, whether that's citizen science, whether that's industry associations, but even on the veterinary sides, and I think you'll back me up here, like, I saw that you talked a lot about all these drugs being sold for pigs. Okay, are they being used in pigs? Because we have a limited number of drugs. Like, Canada is a small market, right? And it's very expensive to develop a label for a particular application. So there's a lot of off-label use. So it's like getting that actual use data. I see a case there for however you want to do it, general population reporting. Yeah.
I guess one thing I'm maybe just a bit skeptical of, you can go down the rabbit hole of trying to get better and better and better data, and I'm just not sure whether it will lead you to better conclusions. And I'm just wondering, with the idea, I think, fair to say that our HydroFATE was to give you an idea of where you should focus. Mm-hmm. And so we're not predicting the risk as so much as directing you to where the risk should be greatest, so that you can carry out targeted studies and identify the contaminants of concern, and from there back interpolate what behavior is going on in your region, which may allow for another intervention. Because the pharmaceutical data, believe it or not, you get it down to the level of a postal code.
Yep.
So we know if you went to that Jean Coutu at that corner, now we may not know precisely who bought it, but salespeople know who bought it in the sense of the general region. But that's many, many millions of dollars even to get data from 3 or 4 years ago, let alone current sales data. Because again, this data is marketed to pharmaceutical companies to direct their marketing strategies for what doctors they need to visit to make sure that their drugs are being prescribed. So there's a huge barrier, a firewall between us who want to use this data and those that actually collect it. And again, I still wonder whether, is it really worth it to go to that level? I'm not 100% sure. So like I would say when Heloisa showed where the pigs were, okay, we know where this is where they're grown. I would say that, well, the first thing to do is start to identify those locations where there's the most intensive operations and focus your field studies there. And based on sales, it might help direct you to what are the things that you should be tracking in those local regions without worrying about whether you have a model that will predict within an order of magnitude whether it was right or not. So modeling, I think it can become an end into itself, and I think we got to be very careful about that.
Yeah, that was more a comment in regards to the what can people contribute that would help us make our work easier.
Understood. Yeah.
Yeah, that it wasn't meant to criticize, but it's like because we really don't, but we don't know, right?
Okay.
And it depends
Fair.
what substance it is. Maybe the pigs is not, but for fungicides, I'm not sure.
Yeah, I totally agree. I think again, agriculture is a whole other mess. That's why we didn't touch it. But just one other thing. The thing that worried me most is that even though we were only accounting for domestic sources, we still saw that the risk could be very substantial even before we account for veterinary sources. That says something.
Thank you. Yes, I think just to add to this, I think that's in general the issue with modeling, right? You make a model, it fits kind of pretty good, but not great. You add more specific things, but then it becomes sort of less of a general applicable model, right? So because you could ask for a million other things like what kind of individual septic kind of tanks do people have? How old are they? Because if they leak or not, they can make a big difference. I think maybe thinking about it more, if you kind of turn it around. So for 79%, the initial model predicted the concentration really well, right? So for these other 21%, if those are the cases, especially where you get more than you predict, right? I think those would be interesting cases to drill in at whatever geographical location or scale you can do that, and look. Okay, is there like a CAFO, what is the acronym for?
Concentrated animal.
Yeah, like a animal production analysis, for example, something like this. So is this a way to kind of look for the unexplained variation by kind of checking for these factors that we know likely contribute a lot, but they're kind of really hard to model, and that can maybe give us an idea about the scale of the problem and how, where exactly we expect it to be a particularly bad influence, maybe. Yeah. Sorry, I went off topic here.
So I'm not a modeler. I'm not talking about the model at all here, just citizen science. But I think in terms of citizen science to improve models and citizen science to improve data, it's always useful when you have large sampling that's geographically dispersed because it's cheaper, it's easier, you can get it sent in and processed centrally. So I think to acquire data like antibiotics in waterways or antibiotic genes in waterways, citizen science could be a useful approach. And I think it's particularly good in a place like Canada because our agricultural industries are supply chain management, and we have these big agricultural consortiums that we can take advantage of for things like this. So if we wanted to collect large-scale data on antibiotics, we just ask the dairy farmers to send every dairy farmer to take a little well water sample or a ditch water sample or a river water sample. So I think Canada in particular has a really strong system to start working in some of these problems and getting data where we can expand conclusions about these things to other areas.
Right. So if we stay a little bit longer with agriculture, so we heard of these the situation that you were talking about this morning, so agriculture is also very cyclical, right? Can a model like this inform on variations over, say, a year of these? And could it help identify specific agricultural practices that could exacerbate exposure or things like this? Although I do recognize that agriculture has not been included yet in the data.
Well, be careful that you push the model too far.
Right.
I mean, certainly in the environmental engineering field, we use peaking factors. So we use field measurements of trends and then create a probability model of what, perhaps in the case of even pharmaceuticals, antibiotics, that there are seasons when they are used to a greater extent than others. And so the question we had discussed at one point is whether we might use peaking factors to actually determine, even if we have average annual consumption, might that correspond? Could you actually kind of predict an extreme level? And of course, such peaking factors would have to be used as well in the case of agriculture, where there's more punctuated application of the pesticides, depending on the stage of growth of your herd and the like. So that would be one way, but it's outside of the model. It's not inside the model itself. I don't know. Do you want anything else onto that?
Maybe I can say something. Your argument, I think, is right that there's a seasonality, a predictability in agriculture. There's growing season. There is seasons when you put your fertilizers out. At the same time, I think we expect, when we model this, to see the exact opposite also. This is on a daily basis. The manure is out now, as you described, happened to be on snow. That's this year. Maybe next year it isn't. There's probably a reason why they put it out today. That's the manure holding tanks are full or something like that. If this would be a slightly warmer spring, the situation would be completely different despite the seasonality. One you will find in the water and the other one you won't. And that's what we expect to be so difficult in modeling agriculture, that it's not following a particular cycle when it really comes to what the effluents will be that go to the stream. So, not sure yet how we can do that. And the model itself, as you have heard, we do have this problem that the model currently is a long-term model. So we are not modeling hydrology even behind it on a seasonal pattern. There would be some modeling. There's ways to mimic that with a seasonality in it, but only if the seasonality is really holding. And I'm a bit doubtful in agriculture that it will follow these clear patterns.
Right. Interesting. So that was agriculture. There's a lot of other changes in our environment. Urbanization is one of them, and it seems that your data align much with urban inputs, at least a priori. Climate change is part of it. How does a model like this kind of a model, but also this kind of information, if I try to broaden it a little bit, not necessarily the model perspective, but how this kind of data kind of help us do this balance, and I'm really stating it as a balance between urban changes, these more global climate changes, in terms of policy and agricultural. How does such an approach help us reach this balance within these forces that impact our environment and impact our exposure to things like antibiotics?
So as we mentioned, the model is fast to run. So if we prepare scenarios, that's how we can see all this picture, put those things together. For example, we have the population. If we have what are the scenarios for the future in terms of how much we will increase, which areas will increase. That can all be included in the model. Also, climate change, we might have a little bit with the discharge, but we can still apply some sort of how much it will increase water or decrease in some places. That those are all things that can be done and then put this all together in different scenarios and compare them and see what are the things that affect the most the concentration of those contaminants.
Just because the mic is here, right? I would like to point out that this model is still a scoping or a screening model. It's not a model that predicts exactly what's happening. And you can call that this is a limitation of the model or also the beauty of the model. It is there for screening. I would go as far as saying I work with climate change for water availability questions as a hydrologist. I wouldn't even know what the main culprit will be of climate change on pharmaceuticals. First reaction is, oh, discharge will change. So we might find higher concentrations because of less flow. Or temperature will change, and maybe that does more. Or sediment transport will change because there is more floods, like short-term thunderstorm type floods happening.
The number of infections will change.
All of this is changing, and we have not studied where should our focus be on this. And that's where I think what Heloisa said comes in. This model can at least try this. We can say we don't know, but we run these scenarios, and we haven't done that yet, but maybe we see what of these effects might be the main risk here.
Given that I think some of you may be aware of these, the recently released Canadian Institute for Health Research released Canada's research priorities for One Health and AMR. Given that literally the top one right at the top of the page is sort of transmission and drivers of AMR, I think this is going to be super useful for guiding us to where we should be doing sampling or where we could maybe need to think about interventions, or at least study if it would be feasible, right? And I think that would, like you said, it would depend on the substance, right? Like it's not going to be the same answer for everything, and possibly even these agricultural chemicals, which it would be really exciting if you were able to integrate that into the model. Because even if it's challenging, the flow within the river would be set, kind of, right? So that at least where things where is this nexus where all of these things collect and where do things really come together? And I mean, we've started to recognize, I think, that sediments are something we should be worrying about, right? So where is it more likely that we're running into those, like a larger concentration of that? So I appreciate your point about this being a screening model.
Oh, good.
One thing I found really striking when I read the paper about your model was the difference between untreated wastewater from urban versus agricultural population and how strikingly different sort of the decay functions are between those two things. So I think that is really interesting because, I think you alluded to, Dominic, thinking about urbanization and populations, going into the future. And this might just be like one of the kind of the easiest lever to go for, right? It's like, okay, you really need to build more wastewater treatment plant in city, or like kind of have not so much closed ground where kind of just waste runs over without having any chance to decay in the soil. So I think that was for me one of the most striking aspects of the model, I gotta say.
Again, I think this is all part of the scenario modeling, right? So from my perspective, if, let's say, there's a policy intervention or regulatory intervention, kind of going back to the birth control work that I'd done before, where imagine a ban on the birth control pill, and then based on personal choices and situations, mapping out on the behavior of 11 million users in United States, it surprisingly showed us that a reduction in the consumption of an estrogen that is emitted actually resulted in a net increase in total estrogens that are out there. So the models can actually show that maybe some of the interventions, coupled with a lot of other information that is out there, may not have the desired effect. But in other cases like this, to say, oh, we need to concentrate our efforts. So we mentioned the idea that maybe if there's limited amount of resources out there, which there is, to invest in upgrades of wastewater treatment plant, where would you use your limited resources to best effect? And so you can pinpoint it, and then you can run the scenario. If we upgraded these wastewater treatment plants for these large urban populations, an example, what is the net reduction in risk and exposure to the populations that are downstream? So this allows you to play with all the different scenarios that are out there, and after playing with all these scenarios, it might guide your interventions in very specific locations. So I think there's a real value here, and this goes to the perspective of One Health, that it's all of these systemic issues that are all linked together that somehow you have to link, of which I think HydroFATE is a portion of that. It'd be really interesting to start playing around with these issues, again, to drive where our research goes, to close the gaps, and maybe look at the interventions that would be most effective.
Good. So, Doug, you've alluded towards policy, and do we know within the panel, as a general, do we know of initiatives around the world where we're trying to control antibiotic residues in surface water? Do we know of any policies like that?
Well, I think in Europe, there seems to be a lot more discussion around this of starting to measure AMR in wastewaters themselves. So there will be a data set that is developed over a period of time, which I think will drive interventions at a later date. So I think they're asking the right question, and they're mobilizing to actually generate the data that will make this possible. Whether that expands beyond the boundaries of Europe is a whole other question.
So I guess my next question would be, how can we go from the scientific perspective and this mapping to the regulators or to the decision makers? How do we make that happen? How do we
end up with this?
How do we get our students to get involved in this maybe?
I don't know that, I think Europe is struggling with the same things that I think everybody is struggling with internationally. I don't think there's huge agreement on what is it we're supposed to be measuring, what's going to make the biggest difference, how do we do it, how can we best work together. I will agree that they are ahead of us by far, and they've done some interesting work on how they can collaborate to do this across, I think, how was it, 15, 16 countries? They just did a trial, EINet. But I think we're all struggling with what is it that we're supposed to do and how exactly are we supposed to do it. So I think we're all watching Europe. But there's also NARMS, the SWAM project in the US. And I don't know if you guys have looked at that at all. But if you're going to look at modeling genes, they did a huge surface water monitoring project. And they've completed a second set of full data. And I think that's coming out. So there is data on this on AMR in surface waters across the U.S. in all these river systems. Actually, a really nice data set. Alison Franklin and her team have been working on that. And we're working a bit on pilot stuff to figure things out, to how do we measure these. We have assays worked out. We're working on measuring things in wastewater. But as you said, resource limitations are there. But there's a lot of work at the federal level trying to build capacity in this area. But for us, speaking for where I work in the public health agency, the priority would be to provide data for people to do things with. And I'm not sure that the regulatory landscape in Canada is really complicated when it comes to this stuff. It's shared between provinces, municipalities, feds. It's so complex. If you are able to inform best management practices and guidance, I'd be pretty happy. I don't think that manure was supposed to be applied at this time of year on those fields, according to current. Give credit to Ontario where it's due. I'm pretty sure that's not that's not a thing.
I was wondering, the public, are there questions that you'd like to address to the panel? Are there things that you'd like to see cleared up? Yes.
I was curious. I think I can speak up loud. I was curious from the data that was presented in HydroFATE. You did the first case study with sulfamethoxazole, and then you went on to actually quite a large number of antibiotics. had like in the top, amounts were a number of antibiotics that were of the beta-lactam class. I was wondering if, looking at the data and all the limitations that you have, can we interpret that list of antibiotics and say, these are the most relevant one or important one because just by quantity there's more of it? Or is the data still too sparse and spotty right now to really kind of even do that kind of triage?
The big issue, like you saw that amoxicillin and cefixime, there's a lot of, when I started presenting that, a lot of people came to me, but those degrade fast. Yes, but there's no studies saying that. I tried looking everywhere for studies saying it degrades fast. It's just papers saying it degrades fast. Well, nobody measures it. And so the problem is that then how could I put that in the model? So that's why a lot of it, for example, for those three top ones, a lot of the parameters were estimated. So there is even though they were the top ones, it has to go with a grain of salt of like, okay, but we have to measure to see if they are there or not. But it's still, we still use the PNAC, so we still use the threshold. So they are, even if they are, they have a large amount, they still are riskier than the other ones as well. Even though sulfametox is always, everybody measures, everybody studies it, but it actually is not that problematic comparing to other ones. So that's why I think the first step is measuring and also studying how those compounds really behave in the environment. That piece is also missing for a lot of them. So I think that would be a good way to just using these results as well, is to, okay, maybe we should study those compounds a little more, even though we're dismissing them for a long time, because they were still measured at high amounts in the rivers. So even though people say, oh, it degrades fast, but it's still there somehow. So, or people are putting even more in it, or it's still not degrading as fast as it's believed.
So I think that's one of the exciting pieces, how this can be like a feedback cycle. As we do that work, you're telling us where to look, then we feed it back in and it refines the model and it gives us a better idea where to keep looking, right? And I think that's great. I think that's going to be a fun way to work on that. Yeah.
Maybe just to say that as much as I'm a wastewater treatment person, the solution is not wastewater treatment. I think it's management practices, and that ranges right back to agricultural practices, but prescription practices for doctors. Kind of going back, I'm an engineer. What expertise do I have in birth control? So when we did this really detailed study, I was delving into a very sensitive area, because some people were saying, why are you, white male guy with gray hair, delving into my birth control practice? So it's a really sensitive thing. But one thing I found, my wife is a physician, works up on James Bay with Cree, and then she graduated from McGill. She introduced me to a lot of people. And we realized at the time the shockingly low amount of training of practicing physicians when it came even to birth control. The limited number of hours, let's say not understanding even how to use an IUD. They knew how to prescribe it, not how to actually work with their patient and monitor, etc. And so I guess my personal feeling is if we identify where these risks are through the model, that the best practice is not to refine the model and not to add more treatment technologies, but to actually go upstream and look at the practices to minimize the use and the dispersion of these pollutants in the first place. And I guess I'm hoping that the model says, yeah, there's a risk. We know there's a risk, and it's a prevalent and very widespread risk. Let's start focusing on prevention as the major strategy that I think we need to work on. That's just my personal view. As much as I love the modeling, and as much as wastewater treatment plant is really fun, maybe not to all of you, I still don't think it's a solution.
Other questions for the public? Yes.
Well, I guess super interesting. Really could listen to a lot more about this. But do you have any sense of how many people are using this model? What sort of level of use has there been so far with the model? Have you got any kind of decision makers that have reported being able to use it to screen or scope, or is there a plan to kind of develop a use case or something like this to kind of help people? Like, it's fun to look at, like you were saying, and fun to explore, but has there been anything beyond the kind of, check it out and see how it...
So the one person that I know applied, it was someone from more of a consulting, so using more, it is still, I don't know if I can say that that's already application of the model. It's still a lot of studying, and it's still, I feel like it hasn't broken the barrier yet. And it could be because it's still very scientific, it's cold, it's not pretty, it's not, and that's why we developed the website with the map, so people could have a little more of a hands-on idea of how it works, and maybe we even had like some like projects on making this more accessible in a way so that people could use it. But it is hard when it's just me, and as much as I work with the code, I'm not a I'm not a computer scientist, so there is a limit on what I can do in terms of. Yeah, so I think what we need is to make it bigger and have more people involved. For me.
Do you collect statistics or anything around usage or?
Oh, we don't even, because we do have our code is on Figshare. People can download it and use it, and it's hard to keep track on that. We have citations on the study, but it's still. So I would feel. Anybody who would really want to use it would have to contact me first. There were some people, and they were all very interested. How do we use it? And then I pointed to because I also have limit of time to coach someone. So there were people that approached me, students, mostly students in general, wanting to use and know more. But I haven't seen anything more than that. Usually when we're approached by companies or it's more they want us to do something, not to use the model specifically. Yeah.
Maybe a positive spin on that is this is really new also. I mean, you have seen it a few times, I know that. Yeah. But it is the first publication, version 1 came out 2 years ago. So it's 2 years out in the open. And to me, it's actually very exciting to see. We have been approached by now by a couple chemical companies who basically start with, we have seen it. And that is something I have not, I mean, maybe it doesn't happen to me as a hydrologist, but I have not seen that industry is approaching us without us poking them. So I think it's realized, it's out there, and they are very interested in seeing what it can do. They want it to do more than what we can do at the moment, so we're struggling a bit with that, but I think it's definitely a very interesting model, it seems, for the producers of these substances also, who also want to understand where their chemicals end up.
That's actually another interesting question and a big black hole that we're facing, I think. I don't know if you guys have seen that Clive Aiked paper, 2019, on a few pharmaceutical companies, and that is, so she measured pharmaceutical effluent, but as influent into wastewater treatment plants then, and there was quite a bit of, there were several substances in there, including antibiotics. So I don't think we have a good handle on how much of that goes, hopefully, into wastewater treatment plants. I suspect it does, from those sources in Canada, because like there is a pretty healthy generic pharmaceutical industry, and even if we're not producing the active pharmaceutical ingredients, often when you formulate them, so you put them into pills, you still got to wash all of that out, and your actually emissions are going to be just as big. So that's another interesting, a really interesting area that well, I for one, I'm quite keen on learning more about. So I'm not surprised that they talk to you. Well, maybe a little bit. No,
That's good. I wonder, like, if I'm coming to you and I'm saying, okay, this is great, I want to use this on this PFAS or something like this. How many data points, what exactly would I need to bring you to be able to run this model in a reasonable way, right? So, because that's kind of like how much, how realistic is it that, I could find a data set or can,
I guess.
Oh, sorry, yes.
I guess we need the use data, the consumption, how
local
much is
consumption,
coming, or even if we want to do a regional model, Canadian model, we need how much is being consumed. Or what we can do is if we have just a huge amount for the whole country, divided, make it some assumptions in terms of population distribution. And then, of course, we need measurements to validate, especially if it's new substances that we haven't done it before. I'm thinking of PFAS. We would need to validate that because it hasn't been used for that. Also, then I don't know how much, depends on, like, would I then have to search for what are the model parameters, like know how much is removed, how much is, or if it is okay to just know a worst case scenario where nothing is removed, but like just to know how much is would get there as a worst case scenario of persistency. So yes, we need a lot of things if we want to do it, like the data availability, but also knowing how much, what are the simplifications that we can do, right? Because, as you said, the model is limited on what it can do. So we need to know what are the assumptions that we can do, and that depends on the goal of the study.
May I just piece that as well?
Yeah.
Kind of going back to scenario modeling. So some of the things that we did earlier on in this work before we got to HydroFATE was scenario modeling based on market penetration. So if you have a new drug that is coming on the market, and I'm assuming that very often the companies, as they go through the approvals, talk about the anticipated level of use of many of these compounds. And so what we were simulating is what would happen if, say, a certain series of drugs was displaced by another drug that came on the market, and assuming that, then predict, based on that level of consumption for communities, how much might end up in rivers. So you use it as a model to maybe even inform the approval processes about what you should impose in terms of limitations on use. Talking to people in Environment Canada, remember triclosan was a big surprise for some. Is that, triclosan being heavily used as an agent to spray it on underwear and things like that, right? So it's being heavily used, and in every laundry washing, it's going down the drains. And so if somebody had done initial triclosan modeling for a range of applications, including the use on textiles and things like that, you can get a sense early on, whoa, this has huge potential to generate a problem. So the scenarios can be not based on existing data, but based on projected data for what you might expect of use. We were even talking, remember pandemic? Well, there was an earlier potential pandemic we were worried about, and I remember looking at some of the Tamiflu and other things like that. So if you suddenly had mass prescriptions in the event of a pandemic, what might you expect to arrive in your rivers? So again, modeling situations before they occur to see whether there's some guardrails you can put on the use of those compounds at the start. And again, I think HydroFATE can help with that sort of thing.
Triclosan, which also co-select for ciprofloxacin resistance, among other things. That's one of the literature. We'll bring this discussion to a close. But